Hey y'all, welcome back to Kelvin's Classroom. Thanks for coming in. So we're going to continue our journey looking at digestion, and we're going to actually look into enzymes and how they work, how that chemical digestion process works. Okay, so if we're thinking about breaking down food, right, we can think about taking it and we can chew it and we can break it down, but you can only get it to a certain size, right? We need it to be really small. We need them to be either monomers or at biggest, we want them to be dimers, where there's two of them attached together for our body to be able to absorb them, for us to be able to absorb them into the body and use them. So how does that work? How can we go about doing this? Well, today we're going to look at three things with enzymes. First thing we're going to look at is what enzymes we have inside our body. Now, we have a lot of enzymes inside our body, so we're just going to look at some of the main ones, some of the really important ones, what their names are, what they work on, where they're found. And then next thing we're going to look at after that is we're going to look at some of the factors that actually have an effect on it. Some things that could speed up how well they work or slow down or maybe cause them to stop working altogether. Final thing we're going to look at is how do enzymes do their job? What is it that they're doing? How is it that they're actually able to do that? Let's go ahead and start. All right. So if we're thinking about digestion, last time I used my apple as an example, but this time we're going to use a little bit more complicated food, right? My amazing artisanal sandwiches. So I've got, my piece of bread, I've got a piece of meat, and I've got a piece of cheese. Now in this, I've got the three different food groups that we typically think about. I've got starch, carbohydrates down here at the bottom. I've got protein, and there is some fat in there as well. And then we have my cheese as well, which is protein and fat. Now, when we think about eating these and chewing these and breaking these down, we need an enzyme that's specific to each of these to break them down. Because enzymes aren't just going to break anything they come into contact and break them down. Otherwise, we could start to see damage happening to the body. We could start seeing things that we don't want. We want to really control that. So let's dive in. So with that, as I take that bite and the food enters my body, starts to travel down, it starts to get broken down physically and chemically. Chemically, in the mouth, that's where digestion starts. We talked about that last time. And what's happening in there is we have our first enzyme, which is called a carbohydrase, which just means any enzyme that breaks down a carbohydrate. Super simple, right? Carbohydrate is broken down by carbohydrase. Now, in the mouth, the specific enzyme doing that is called amylase. Amylase. What it does, it takes starch, which is, imagine I have lots of tiny little sugar molecules all attached together, stored together by being compactly bound together, tied together. It's taking those and it's going and it's breaking them down into smaller pieces. It's breaking them down into maltose, which is two pieces of sugar attached to each other. Now, the food's not in the mouth very long, so it can't do that for very long. So it starts that process, but it's not complete. It doesn't fully finish that. It travels down into the stomach. Once it gets into the stomach, all of the work that the amylase was doing is going to stop because it's going to get into an acidic environment. And we think about acid, we think about it changes things. So if we want to imagine a really bad movie and we imagine someone pouring acid on something and it just melts away, right? That's kind of what's happening with the enzymes. The enzymes go from a neutral environment in my mouth into an acidic environment inside my stomach, and they break. They change their shape till they're no longer able to work. We call this denaturing. Now, what denaturing means is just physically changing the shape of it so it's no longer able to keep working, right? We never refer to it as killing it because a protein isn't a living thing. Because an enzyme isn't a living thing. It's just a type of protein that's put together in a way that it serves a job. It's like a tool. It is a basic tool that serves a job. We can't kill it. I can't kill a hammer. I can break a hammer. I can't kill an enzyme. I can denature the enzyme. So in the mouth, amylase is working, breaking down the starch. It's the only food substance being broken down in the mouth. Now, a way to help remember this. Now, I know what you're going to be thinking. You're going to be saying, Kelvin, I don't want to do that. That's weird. That's gross. It's all right. You're probably in the privacy of your own area. No one's around you right now. No one's going to see it. So what I want you to do, hit pause, go and grab a piece of bread. Got it? Good. Now we're going to test out and see how well our amylase is working inside our mouth and if it's actually working. So when we get a piece of bread, it's starch. It's mostly just starch. And so if it were to be broken down, it would turn into, eventually, a simple sugar, sweet tasting. Now with a piece of bread or a French fry or a baked potato, it doesn't taste very sweet. It kind of tastes fairly boring and bland. So we want a bland piece of starch. What we're gonna do, we're gonna start with this, you're gonna leave it to the side, and we're gonna come back to it at the end. What I want you to do, take a bite of it, you're gonna chew it up for a minute, but don't swallow it. You're not gonna swallow it, you're gonna put it on a plate and set it to the side till the end of this video, and then you're gonna come back to it and we're gonna see how it tastes. All right, so let's go ahead and do that. I'm gonna grab my plate to put this on. Chewing it up. All right, then we're gonna put it on the plate and store it for later. All right, we're gonna come back to that later and see what's happened as we're not doing anything to it, just the saliva's working on it. We're gonna see how that affects it. So the amylase gets to the stomach, it breaks and stops working, but I told you last lesson we were talking about how there are enzymes in the stomach. Now the enzymes working in the stomach are breaking down proteins. I want you to take a guess at what you think we call those enzymes that work on proteins. We call those protease. We don't get too complicated. Carbohydrates, protease, we're keeping it simple here. So protease are the enzymes that break down proteins. Now, we do have a few different types of proteases throughout the body. Depending on what curriculum you're doing, you might want to learn it. So some of the ones we learn are Pepsin or Peptidase. Those are some of the ones we learn about, but we call them all together proteases. Now, in the stomach, our proteases start breaking down protein. So in that sandwich we ate earlier, right, we had the turkey in it, which had protein in it. That starts getting broken down inside the stomach. So it's being broken down. Nothing else is really being broken down other than the physical churning that's happening in there. It breaks down for a while, and then it leaves the stomach and gets into the small intestines. Now, as we remember, when it leaves the small intestines, we neutralize it with that bile, which is going to, what's it going to do to the protease? It's going to denature it. It's going to break it. It's going to cause it to change its shape, no longer be able to work, because acid has the ability of breaking the shape of it, but also if I go from acidic to alkali or neutral, it's going to break the shape of it as well, because it's a new environment. It just changes the shape and breaks it, so it's no longer able to work. So now we have those amylase that got broken and the protease that got broken that are no longer doing any work. This is where the pancreas comes in. The pancreas is going to make amylase, which breaks down carbohydrates, protease, and lipase. What do you think lipase breaks down? It breaks down lipids, which is the group that we call fats and oils. We put those two together and we call them lipids. The only difference between the two is fats are at room temperature, they stay solid, and oils at room temperature are liquid. Other than that, there are some differences that as you continue on, we'll look at, and we'll explore what some of those differences are. But for now, we can just break them up into those two groups by one is solid at room temperature, one's liquid at room temperature, but they're both a form of a lipid. Now, lipase breaks down these lipids, starts breaking them down into smaller pieces, as well as the carbohydrates and the proteins. So as it's moving through the small intestines, we have proteins, carbohydrates, and lipids all being broken down into smaller pieces so that way our body's actually able to absorb them. This continues happening all the way through till it leaves the body. We've broken it all down, we've absorbed everything we need from it. So as all of these enzymes are breaking down the different food types, what's actually happening? Well, we know where the enzymes are. We need to see how they're doing their job now. Now let's imagine a key and a lock. Now, if I have a keychain full of different keys and I'm trying to get into a door, I can't just use any key. They're not gonna work that way. I have to have a specific key for a specific lock. The same works with enzymes. I need to have the exact enzyme to break down the exact substance that I'm trying to break down. Now, we call this the lock and key model because enzymes fit or match to a substance that they're breaking down, just like a lock matches to a key, right? Now, it's not exactly correct, and as we continue on, we'll learn about the induced fit model and how it's a little bit better at deciding it, but for now, it's really good just to understand that an enzyme and a substrate, which is the substance we're breaking down, are like a lock and a key. They're complementary, they fit together, and they allow us to break it down. Now, if we were to choose one of those and see how this happens, let's start with a simple one. Let's talk about carbohydrates, so amylase, and a starch. Now, a starch, if we want to visualize it, we can just imagine a pearl necklace, right? Now, imagine we break that pearl necklace and we just hold it and let it dangle there, and it's a nice long string of beads or pearls. And we can then take our enzymes, which are kind of like our scissors, but they're specifically designed just to match to it. And it comes along and my substrate or my starch gets attached onto by my enzyme, and that enzyme then physically causes it to change shape in the starch, which breaks the bond. And now instead of having one long chain, I break it up into two. And then it comes along and finds another spot and breaks it up again. And it repeats over and over and over, breaking up each of those individual bonds where they attach until I have a handful of just pearls or beads or whatever, because they've all been broken up. Now with the starch, it's individual glucose that's been broken up. I break it down into really small individual glucose, so I have all of them separate, and then the body can easily absorb that. So how it does that is in a couple steps. Inside the mouth, the amylase breaks it down, like we talked about, into those individual or those double pieces that are attached together. Then it gets into the small intestines, and we start to see it break down even more. It breaks up in two phases. One is amylase, which is breaking it up into maltose, which are pairs. And then we have one called maltase. Look at that word maltose, look at that word maltase. It keeps it simple. And it comes and breaks those pairs into individuals. And then we can absorb it into the body as glucose, which is what we really want as that energy source, right? So if we were to look at it, our starting point, our substance, our substrate is starch. Our ending is either maltose or glucose, which is what our body can absorb then. Now, when they're combined, when I have that substrate and that enzyme combined, we give them a different name of an enzyme substrate complex. And all that is saying is it's during the time where they're connected, where they're attached to each other and actually working. And then at the end, when they separate, my enzyme, it's the exact same. It's not changed. It's still like it was in the beginning. And the two pieces that come off now are called products. Now, an enzyme can go either way. We can take an enzyme to break down starch or to build starch. Enzymes, all their job is to find what matches them and then do work on it, either breaking it or putting it together. Now, where this connection happens when they attach is called the active site. Now, the active site on the enzyme is perfectly designed to match up with the substrate that they're attaching to. That's how they know and can connect with each other. They're not magic, they're not living, remember, so they're not searching it out like a dog. They find it, they bump into it in the right way, then they attach, and then it physically causes them to change shape. Just like the key is not living, it's not looking for the lock, it just has to make its way into the lock, facing the right way, be the right key, and it can do its job. So that's carbohydrates. Let's go ahead and look at protease next. So protease breaks down our proteins. Now, proteins can come in lots of different shapes and sizes. We're not going to stress too much about the different shapes and sizes they can be, because when we look at protease, it finds the connections between two different amino acids. It goes in there, connects, and breaks them apart into their individual amino acids. Now, all an amino acid is a building block or an individual unit of a protein. There are lots of different amino acids we could have, and at this point, we don't really need to know all the names of them. Far too many of them. Let's not stress about it. Let's just think an amino acid is the building block. When I combine them, it makes a protein. The protease comes along with its specific active site, finds the complementary shape that is attached. That's the amino acids combined in the protein. They connect, they break apart, and then it releases it and goes on to find a new one. Our last one is lipids and lipase. Now, these are a little bit trickier than the other two. So when I think about a lipid, I think about a fat or an oil. Now, they aren't just a chain of different pieces attached together. Instead, I have a glycerol backbone, and I have 3 fatty acids attached to them. Now, these fatty acid chains are attached, they're kind of like tails. You can almost imagine it kind of like an octopus, but instead of having 8 legs, it just has 3 legs. And the lipase comes along, it attaches to that point where the fatty acid chain is attached to the glycerol, and it breaks them apart. And then it releases it, and it goes and finds a new one and does the same thing. That way it can release those. Right? So these are the 3 main enzymes that we have, how they break things down, what the substrate is, what the product is as it breaks it down. We have a pretty good idea of how it does this by breaking it down just by physically changing the shape. We understand that when that shape is broken, it's called denaturing, and it can no longer keep doing its job anymore, right? Just like if I take a hammer and I break it, it can no longer do its job. The last thing we said we were going to talk about is what things can cause it to do faster or slower to do its job. We're going to talk about 4 different things that can cause it to speed up or slow down its job. The first one we're going to talk about is temperature. Now, if an enzyme is just a tool, it's not living, it's not able to make decisions, it's just kind of like a tool floating around trying to do its job, as we increase the temperature, how is that going to change what it's doing? We can think back to when we talk about physics and particles and how temperature change causes it to change, right? So let's imagine that I am a particle in a near 0 degree temperature. I'm moving, but very little. I'm kind of sitting stationary. And as I start to warm up, I start to move faster and faster and faster until it breaks free. And that's when it changes into a liquid, and then it speeds up even faster until it can break free into a gas. Now, if we think about that and apply it to an enzyme, the same thing's going to happen. As I add heat to an enzyme or to the substance that it's in, it's going to start traveling faster and moving around faster, which means it's going to have more collisions with different things, which means it's going to more frequently find the substrate that it's looking for and interact with it, right? If we imagine I put a blindfold on and I'm walking around the room, just bouncing into the wall, and I'm holding a key in my hand. And I'm waiting until I just perfectly bump into the wall where the door is and the key slides into the hole, right? If I'm walking really slow, it's going to take a long time for that to happen. If I'm moving faster, it's going to happen quicker just because I'm colliding more frequently, right? The other reason this speeds it up is when they hit, they have more energy, which can speed up that reaction. Now, what happens if I heat it up even more? So let's go back to that example of I'm walking around with a blindfold bumping into the wall. Let's imagine I keep speeding up. Eventually I'm going to be going fast enough that I'm going to hit something and I'm going to get hurt or I'm going to break the key. The same thing happens with the enzyme. If it gets too hot, it's going to cause it to physically change its shape. It's like it's melting there. It changes the shape, the bonds inside it break, it no longer can do its job because when it bumps into the substrate, it's not the same shape that it originally was. So it can't do its job anymore. So when we think about this, what we think about is as we increase temperature, the rate of reaction, how quickly it's breaking things down, starts to increase, and then it hits an optimum temperature where at this temperature, it's able to keep its shape, but it's moving as fast as it can. Any faster, we see it denature. And remember, once it denatures, it can't do its job at all. Not just slower, not at all. So it drops straight back down to having a rate of reaction of 0, where it just can't do its job. Now let's think about a different setting. Let's think about changing the pH in it. Now, pH is different to temperature, right? Because a pH scale isn't going from 0 being neutral, and then the higher we get, the worse it gets. pH has 7 as neutral, right in the center. And as I get lower, it becomes more acidic. And as I get higher, it becomes more alkali. Now, even though we normally think about acid as the thing that destroys and melts things, both acid and alkali are corrosive. They will destroy things. So I might think then, perfect, all my enzymes want to be at exactly 7. That's where they're going to work best. But we talked about one being in the stomach. That's not going to be a neutral environment. So each enzyme has an environment that it's happy, an environment that it likes to work in. For our stomach enzymes, that's going to be at 2, because that's what the stomach's setting is like. For our mouth enzymes and our small intestine enzymes, it's going to be at about 6.8, because that's where they work really well. And if we look at that, that's where they are most effective. We call that their optimum pH. And if we go either direction, either making it more acidic or more alkali, what we see is it starts to denature, it starts to break, it stops working. So with this, what we'll see, we have optimum pH right here at 6.8 for amylase. Either direction, it quickly denatures and it stops working. With the stomach, it's at 2, and we go either direction, and it quickly denatures and stops working. So 2 factors we've talked about. Temperature, cold temperature, it's not going to cause it to break, it's just going to slow it down or stop it, and it won't have enough energy to do its job. As it speeds up the rate of reaction until it causes it to denature, and then it stops. pH has an optimum pH, either direction causes it to denature. We're going to look at 2 more different factors that can affect it. And if you know me at all yet, you'll know we're going to use food as an example here because I like food. So for these, we're going to talk about concentration of enzyme and concentration of substrate. We need to understand what those 2 things mean. Concentration of enzyme is talking about how many enzymes are present, right? How many enzymes are there? Is there little of them or a lot of them? So we're going to look at that one second. The first one we're going to look at is concentration of substrate, which is how much of whatever I'm trying to break down is present. In our example, let's imagine that I am sitting at a table at a pizza buffet. All right. Now, for some reason, this pizza buffet doesn't let me go up and get my own pizza. They bring it to me. And they're going to bring it to me not one pizza at a time, not even a slice at a time, one bite at a time. They bring me out a plate with one bite on it. And I eat that bite pretty quick, and then I sit and wait for them to bring me another one. And I eat that bite, right? Think about how quickly I'm eating. It's pretty slow. I'm waiting on there being food available for me to eat. It's going to take time. Now, they catch on and they say, we better get him food faster. Let's bring him a piece one slice at a time. So bring me a slice of pizza and I eat that. And then I wait for the next slice and I eat that. Now I'm eating it faster. My rate of reaction has increased, but I can still go faster. So they bring me a full pizza and then I start eating, right? And then they go, ooh, even more. And they bring me 2 pizzas, 3 pizzas, 4 pizzas. Eventually, I'm not going to be able to eat any faster. I'm going to be eating at my fastest possible rate of consumption. My rate of reaction is going to level out. I'm going to be eating as fast as I can, and there's always more pizza available. That's what happens with enzymes, right? If there's not very many substrates around, they're kind of just looking and waiting for substrates to interact with. As more and more become available, they start reacting quicker, and then pretty soon it's like there's a line waiting for them, and they're trying to get to them, but they're just going as fast as they possibly can. So with this, what we would see is a rate of reaction that increases, and then eventually you hit what we call a point of saturation, where there's more than enough substrates, there's all that we could possibly want, and it levels out. It can't go any faster. It's not going to cause it to denature or break. It's never going to slow back down. It's just going to stay at that rate then, where it's working as fast as it can. Now, let's imagine that situation again, where I've got lots and lots of pizza there, but I decide I don't want to be eating on my own. Instead, I invite a friend. Now, as that friend comes and sits down next to me, it's like I have more enzymes. We're going to all of a sudden be eating faster, right? So our rate of reaction will increase. And then we bring another friend until all of a sudden there's 20 of us there sitting at this table and we're all eating. Our rate of reaction is going to be a lot faster. Well, now the kitchen's trying to keep up making enough pizzas to keep us satisfied. We keep running out of pizza because there's so many people eating the pizza. That's where we see, again, we'll call it a point of saturation, where the rate of reaction increases until there's so many enzymes that there's not enough substrates to keep up and we start going flat again. It doesn't go back down, right? Because they're doing reactions. There's just so many enzymes that they're interacting with everything there is available, and they're waiting for more food to come. Okay, so these two have the same shape, but both of them reach a top where it's point of saturation, and we're not going to see any denaturing with these two. These are the 4 factors that can affect the rate of reaction. We can see them in lots of different environments. We can see how they're doing different things. And what we want to see is an enzyme working at its optimum conditions. And what that means is it's at the right temperature, it's at the right pH, it has enough substrates available for it to do its job, there's enough enzymes available for it to be able to carry out the reaction. Now, the last thing that we need to think about is, great, I know where enzymes are, I know what enzymes there are, I know what they do, I know how they do it, I know all of that, but what is an enzyme? I don't know how I could answer a question if it was, what is an enzyme? So let's simplify that down. An enzyme is a protein, right? It's a protein that catalyzes or speeds up a reaction. That's what it is. A protein, meaning that it's just a combination of amino acids put together into a specific shape that can then do a job. Remember, that's the hammer. Catalyzes or speeds up a reaction. Sees something that's going to happen and it helps it along. It speeds it along. It gives it a boost in doing that, so that way it can carry out the reaction at a faster rate. And at the end of it doing its job, it's unchanged. It can continue on doing its job. A hammer can hammer one nail in, and then the next nail in, and then the next. An enzyme can break substrates over and over and over. That's it for enzymes today, guys. Thank you guys for sticking around. Come back next week. We're going to continue on. Next week, we're going to look at some of the foods that we've talked about and how you can test for different foods and why that matters, being able to test for it, and some of the ways we can apply that. As always, please like, subscribe, share, throw a comment or a question if you have anything to say down there in the comments. Really appreciate you guys coming back, and I'll see you guys next time. Thanks.